Hello and welcome to episode 10 of Astromagnet. I'm Arush Ramadurai,
And I'm Ishan Chakrabarti.
and today we're talking to Professor Maura McLaughlin, Professor of Physics and Astronomy at West Virginia University, and a member of the Pulsar Search Collaboratory team.
Welcome to the podcast, Professor McLaughlin. To start, how did you first get interested in astronomy, and why are you interested in it?
Yeah, so first of all, thanks for having me on your podcast. I guess it's easier to talk about how I first got interested in it to start. When I was a kid, I read a lot, like lots of science fiction. So I never was an amateur astronomer. I don't know any constellations. I sort of came at it from more like a sci-fi perspective. Like, are black holes really cool and things like that. And then I read a book by Stephen Hawking, which I'm sure you've heard of, A Brief History of Time, when I was in high school. And I read that book and I was just so fascinated by like black holes and neutron stars and space-time and all this. And that's when I decided to do physics or astronomy. And then I went to Penn State as an undergraduate. And I was lucky enough to do undergraduate research with a professor named Alex Wolshin, who had just discovered the first extrasolar planets. And these were planets orbiting a pulsar. So I started studying pulsars when I was an undergrad. And I just thought it was amazing that you could detect, signatures of planets around a pulsar through radio observations, through radio timing. And I've kind of just done that same kind of research ever since I was an undergraduate. I just became really fascinated with pulsars, and I'm still studying them today.
Can you talk about some of the education that you got that specifically prepared you for like pulsar research?
Yeah, that's a good question. Pulsar research is kind of like an interesting field because it's kind of in between like fundamental physics and astronomy. So you need to understand astronomy because we need to understand like how stars evolve, how pulsars are born, how they move in the galaxy, what the gas is like in between us and the pulsars. We can probe the interstellar medium. So there's lots of like really core astronomy concepts you need to understand. And I took a lot of astronomy classes as an undergraduate and a grad student. However, a lot of the stuff that I do with pulsars is really more like fundamental physics. So not astronomy, but more like tests of general relativity or constraints on like what neutron stars are made of, which actually goes back to like particle physics. So there's lots of branches of what I do that touch on all different parts of physics. So like equations of state of dense matter, and there's lots of math, and of course in general relativity there's a lot of math and modeling. And another big part of what I do is high precision timing. So like measuring arrival times of pulses from pulsars and fitting them to very complicated models. So there's also a lot of like statistics. So like Bayesian inference and basically how well can we fit a model to data and kind of, model all the processes that we see. So there's a lot of that kind of like statistics and time series analysis that goes into what I do too. So I've had classes in lots of physics and astronomy, some statistics and math, and all of that's really important for pulsar research, I think.
Can you talk to us a little bit about what a pulsar is and why they're important for us to study?
Definitely, yeah. So pulsars are neutron stars. Neutron stars are formed in supernova explosions when massive stars reach the end of their lives. They can't support themselves against the collapse of gravity anymore, and they leave behind a very compact core. So for stars that weigh between like 8 and 20 times the mass of the sun, this explosion will leave behind what's called a neutron star. So these stars are very, very dense. They're about 20 kilometers across. So you could fit them inside, a city, and they weigh about 1.5 to 2 times the mass of our sun. So they're basically the density of an atomic nucleus, but on like a much larger scale. Because of conservation of angular momentum, they rotate very rapidly. So they can rotate as fast as milliseconds. So they're spinning very rapidly. They're the size of the city, and they weigh more than the sun. They're really, really exotic objects. We call these objects pulsars because they have very strong magnetic fields, and particles are accelerated along their north and south magnetic field lines. And then as they rotate, every time one of these beams, these magnetic field beams, passes our line of sight, we get a radio pulse because these accelerated particles produce radio emission. So that's why they're called pulsars.
So can you talk about how you helped discover the first known double pulsar system in 2004?
So lots of pulsars are in binary systems with other stars, which means that they're orbiting another star, like many of the stars in our galaxy. And these systems are really interesting to try to discover because we can learn about like the binary dynamics. We can measure the masses of the stars in the system. So whenever we do a search for pulsars, we're always trying to detect these binary star systems. Now, back in 2003, we knew of a bunch of binary star systems, and a couple of them, the most interesting ones, were pulsars in orbit around other neutron stars. And the reason they're so interesting is they're very, very relativistic. They move very, very rapidly because they're two like supermassive objects, and we can test general relativity using these systems and do all other kinds of neat like physical tests. So I was involved in a survey with the Parkes telescope in Australia in the early 2000s, and we discovered a pulsar with a 22 millisecond spin period, and we could tell that it was in orbit with another star. We could see the Doppler shifts of its period around the orbit, and we could see it was in about a 2.5-hour orbit. And from measuring those Doppler shifts, we figured out that the other star must also be a neutron star, right? It had the mass of a neutron star. So that was exciting. This was another double neutron star system. About 6 months after we found the first pulsar in this system, we detected another signal, another periodic signal that seemed to be coming from the same distance, but with a period of 2.7 seconds. So much, much longer than the period of the first pulsar. And from timing the arrival times of both of these pulsars, we could tell that they were actually in orbit around each other. And so this was the very first time that a double pulsar system was detected, that two neutron stars in orbit around each other, both of them detectable as pulsars, had been found. And this was really exciting because if you can measure the signals from both pulsars, you can get a lot more information than you can if you just have like one detectable pulsar. And so we're still timing this system today. It provides amazing tests of general relativity. Plus we see all these really neat interactions between the two pulsars in the system.
Could you also talk about your work with the NANOGrav Collaboration?
Sure, yeah. So NANOGrav stands for the North American Nanohertz Observatory for Gravitational Waves. It's a collaboration of astronomers in the US and Canada who are using radio pulsar timing to try to detect very low frequency gravitational waves. So gravitational waves have been detected with LIGO, right? So this is a ground-based interferometer. It's sensitive to gravitational waves with frequencies of like hundreds of hertz. So signals that happen within time spans of less than a second. Our experiment is similar to LIGO, but we're using pulsars to try to detect gravitational waves with periods of like years to decades. So we monitor a network of these radio pulsars distributed all over the sky with really large radio telescopes. And we search for very small perturbations in the arrival times of the pulses due to gravitational waves. So gravitational waves like stretch and squeeze space-time, which causes the apparent periods of the pulsars to get shorter and longer with time. And so we search for this effect in our data. And so it's a really big project. We've been doing it about 17 years now. And the current status is we see a signature among all of the pulsars, like a common signature that we can't explain, which could be gravitational waves. So it's really exciting, but we can't yet prove it's gravitational waves because we need to see a very special spatial correlation in the data. And so we're searching for that right now. So I'm really hopeful that very soon we may actually have detected gravitational waves through this pulsar timing method.
Sorry, could you talk a little bit more about that common signature and why it's important that we study that?
Yeah, so gravitational waves have a quadrupolar correlation to them, which is a very unique spatial signature that only gravitational waves have. And so what this means is that if I am studying two pulsars in the same direction of the sky, if the pulse from one arrives late, the pulse from the other will also arrive late. They'll be correlated. If they're separated by 90 degrees because of this quadrupolar gravitational wave signature, their arrival times will actually be anti-correlated. And so this is a very special signature that would allow us to discriminate the influence of a gravitational wave from, say, other things like maybe a clock going wrong at the observatory or the interstellar medium or noise that's intrinsic to a pulsar. So we have to observe the signals from all the pulsars and we cross-correlate all the arrival times of all these pulsars across the sky and look for this like very, very special spatial correlation which really only could be due to gravitational waves. And that's sort of like the smoking gun for a gravitational wave detection. We have to see this spatial correlation to know that it's gravitational waves and not something else that we're just not like modeling correctly in our data.
Do you know what causes the gravitational waves? Like, are they related to the pulsars in any way? Or is it like something else?
Great question. Yeah, that's a really good question. So pulsars in binary systems do emit gravitational waves themselves, but we're not searching for gravitational waves from the pulsars. The gravitational waves that we're sensitive to, we think, are most likely going to come from very, very massive black holes. So like millions to billions of times the mass of our sun at the cores of galaxies that have merged. So we're sensitive to binary black holes that are really, really massive. The cool thing about this is that through our detection of the signature of these emerging supermassive black holes, we'll be able to understand how galaxies have grown and how they've merged like throughout cosmic time, all the way to the Big Bang through this experiment. So we're not really studying the pulsars themselves, we're just using them as tools to detect these merging black holes at the cores of galaxies.
So you're also part of the Pulsar Search Collaboratory team. So could you talk about what that is a little bit?
Yeah, so the Pulsar Search Collaboratory, or PSC, as we call it, was founded back in 2008. So it's been going on quite a while now. And what it is an education and outreach program, which involves high school students in the search for pulsars. And we need people to help us gauge like whether they're real signals or not. And it's also been great for the students. The students get a chance to, not just like play the role of a scientist, but really, detect new astronomical objects for the very first time.
What sort of interesting discoveries have come out of the Pulsar Search Collaboratory?
Yeah, so far students have discovered 7 new pulsars. And of those new pulsars, they've actually found quite a few interesting ones. One of them is a double neutron star binary, and there's only about 20 of those known. So that's a binary system with 2 neutron stars orbiting each other. So that was pretty cool. One of them is a millisecond pulsar, which means it's a very fast spinning pulsar. These pulsars have been recycled. So they're pulsars that have lived their whole life and they've been spun up to really short periods from accreting material from a companion star. So that's pretty cool. One of them is what we call a rotating radio transient, which is like a very sporadic pulsar that we just detect the occasional pulse from. So they found a bunch of interesting, for only 7 pulsars, there's been a high fraction of like interesting pulsar systems. And students have participated in writing papers on these systems. They're authors on peer-reviewed scientific publications. So it's been really cool.
So how can interested high school students get involved in the PSC?
Yeah, it's really easy. We have a website. It's called pulsars.nanograv.org. Students can go there and they can sign up to help us search for pulsars. There's a 6-week course that we do every fall and spring. We're doing one right now. We meet on Thursdays at 7 p.m. And so we'd like students to do this course before they start analyzing data. But they don't need to do it, in the 6-week period that we're offering it. Like everything's recorded, it's all online. Students can work through it at their own pace. And then they'll take a pulsar certification test, which shows that they know how to look for pulsars in the data. And if they pass this test, then they get access to data from now just the Green Bank telescope, but we're hoping to expand it to data from lots of telescopes around the world. And they can have a chance to really discover something new. Right now we're in kind of like a transition. We were called the Pulsar Search Collaboratory. We're morphing into the Pulsar Science Collaboratory. So what we're trying to do now also is give students the opportunity to not just search for pulsars, but also do lots of pulsar related research. So we have a couple of research projects going on right now where students take their own data with the 20-meter telescope at Green Bank. We have Jupyter notebooks that we're working on with students to actually do some real like scientific analyses in addition to the pulsar searching. So I think there'll be lots of opportunities over the next few years, both for searching for pulsars and doing some other different types of science experiments.
I guess moving now into a more general look at your career, what challenges would you say that you run across, throughout your career, and how did you approach those?
Wow, what a good question. I guess there's both personal and professional challenges. As far as personal challenges go, I've had a pretty good path, I think, to where I am today. But, astronomy is hard. There aren't that many radio telescopes in the world. So there are only like a few places to live and go, if you want to be near one of these big telescopes. That's kind of dictated my career path. I was a grad student at Cornell, which ran the Arecibo Observatory in Puerto Rico. And then I was a postdoc in England at the Jodrell Bank Observatory, another big telescope. And now I'm here in West Virginia, very close to the Green Bank Telescope, which is the largest telescope in the United States. So my career's kind of followed these large radio telescopes around, and I've been really lucky to be able to stay in the field and be kind of in good places to do astronomy research. My husband's also an astronomer, so that's been like a personal challenge at times. Just, it's hard to get jobs together and both be in positions in the same place. We've been lucky here at WVU, though, to both have jobs in the Department of Physics and Astronomy. Professionally, I've been really lucky to always have, lots of interesting things to study. The field of pulsars is never boring. Like, there's so many things we don't understand, and there's just so much work to do. So I think my greatest professional challenge is just like managing all the exciting projects and science that there is to do around pulsars. I think I really enjoy my job. It's the main challenge is just kind of figuring out like what the priorities are, right? There's just like so much to do.
So much of your career has been dedicated to studying pulsars. What would be major questions that still exist about them that have motivated you to study them?
What a great question. So talking about like pulsars themselves and not sort of the broader like gravitational waves or what we can do with pulsars. There's a lot we don't understand about pulsars themselves. We still don't really have a good understanding of exactly how their emission works, like how they produce their radio waves. We don't understand why some pulsars turn off and on, whereas some are really, really steady, why some pulsars are really bright and others are really faint, why some have high magnetic fields or low magnetic fields. Like, we really have a pretty poor understanding of how they work. And this is a very difficult topic to study. We're talking about like really relativistic plasmas and very high magnetic fields. The physics is super complicated. So I've been very motivated by that. It seems like every time we find a pulsar or someone comes up with a theory that explains things, then we find another pulsar that doesn't fit that theory or doesn't fit that rule. So we just really don't understand how they work. And that's pretty cool. Another big thing that we don't understand is what they're made of. So we know they're neutron stars. We know they have a lot of neutrons in them, but they might have other kinds of exotic particles in them. We just really don't know what they're made of, actually. And so one thing that I do with my collaborators in NANOGrav is try to measure the masses of these pulsars to figure out like how massive one of these pulsars can be, to try to put limits on what they're made of. So we recently measured a neutron star mass that's over 2 times the mass of the sun. That's the highest that's ever been measured. And so finding these objects that sort of like push the limits, right, on properties that we've measured before is really interesting. And there's a lot of physics that comes out of that. I could go on and on. I mean, there's so many things that are interesting to understand related to pulsars, but those are probably 2 of the big ones.
So is there any advice you'd give to students who are interested in a career track in pulsars, or just really astronomy in general?
Yeah, that's a good question. I would just say I think astronomy is a really great field to go into because there's a lot that we don't understand, so you'll never be bored. And the next couple of decades is going to be really transformative. So there are, so JWST is a very large optical telescope that's going to just really revolutionize our understanding of the universe. There are also a lot of large radio telescope surveys happening that can look at like really wide fields of the sky and detect all sorts of transient objects, so objects that come on and off that we've never seen before. Right now we know of 3,000-ish pulsars. There will be some like large field surveys over the next decade, maybe with something called the square kilometer array, which will be a whole kilometer of radio collecting area. And so that number might be 10,000, in another decade. And I think when we detect gravitational waves, that's also going to be another huge moment for pulsar astronomy. We'll be able to start like mapping the gravitational wave sky and really figure out like how galaxies have grown and evolved over time. So there's something for everybody. You know, if you're a person who likes building things, there's lots of new telescopes that need talented people to build like very sophisticated instrumentation. If you like visualization and modeling, there's logging and visualization. If you like math or statistics, these data rates are huge. We're dealing with massive quantities of data. So there's lots of like kind of data science applications, and of course, lots of physics. So there's room for everybody, I think, in astronomy, like regardless of what your interests are or your skill set. We also really need people who are great communicators, right? Who can like explain science really well, write about science really well, and like bring it to the public. So yeah, I think that would be my advice. Is the future is bright, and there's room for sort of everyone with all sorts of different skill sets in astronomy.
Would it be all right if interested high school students contacted you for advice or guidance via email?
Sure. Yeah, that's definitely fine. I guess you can attach my email to the podcast. I won't say it right now because it'll be easier just to, you know, put it next to the podcast, I guess, but that's great. Yeah, they can also join the Pulsar Search Collaboratory program. And when they join that program, we have an online forum that's part of the program. So they can meet other students. They can ask questions, not just of me, but other astronomers, and also of undergraduate and grad student mentors in the program. So there's lots of means to learn more about pulsars and communicate.
Well, thank you so much for your time. So that was Professor McLaughlin, and to learn more about her field, check out our website for additional resources.
Thank you.
So
And
much.
thank you, Professor McLaughlin. We'll be back next time with another episode.